Great. So, hello everyone. Thank you for joining the seminar today. And it's my pleasure to introduce Thalia Traianou, who I know quite well. And she's doing some exciting research that she's going to talk to us about today. Thalia did her master in the Aristotle University of Thessaloniki. And afterwards, she became a PhD candidate at the MPIFR in Bonn, but we were actually working in the same office for some years, working on challenging VLBI data and whatever comes your way when you're a PhD candidate. After her defense, she went to be a postdoctoral researcher at the Instituto de Astrofísica de Andalucía in Granada in Spain. And later, where she moved to her current position, where she's now at Heidelberg University at the Interdisciplinary Center for Scientific Computing. She's also been for some time the outreach coordinator and AGN working group coordinator in the EHT collaboration. It's just one of the many roles that she's inhabiting right now, so very busy indeed. And yeah, let's say without further ado, you can start presenting, and the floor is yours, Talia.
Thank you very much, Felix, and thank you for inviting me. I'm very happy being here today. Let me, okay. Yes, here we are. Okay, let me start with a short introduction about physics, black hole physics and jet physics a bit. Around 100 years ago, we had from Albert Einstein, we had some nice predictions about how light behaves around supermassive black holes. And supermassive black holes, as we probably all know in this room today, are one of the most fascinating objects in the universe. Around these objects, physics behaves with the conditions are very extreme, and physics touches its boundaries. The physics we know that it's boundaries. So it's an ideal laboratory in order to test our theories about gravity and how light behaves in such extreme environments. One of the main predictions of general relativity was that light is creating a photon ring around a supermassive black hole with a flux suppression in the middle. And here I have a very nice visualization in order to better understand the concept of light behavior around supermassive black holes. So theoretically, someone would expect to see something like this around such an object. And there is also an inside joke that the worst place to hide in universe is behind a supermassive a black hole in general, because the light is bent and projected in front of this object. So this was a prediction. On top of that, because of this prediction, we know that the size of this photon ring carries some very important information about supermassive black holes. That shows us, for instance, if we are dealing with a non-spinning black hole, the diameter of the ring is very precise, whereas if we see a smaller ring diameter, corresponds to a rotating black hole. So with this prediction in our mind and increasing our resolution would be a very important piece of the puzzle of understanding black hole physics and later on jet physics as well. So we keep this in mind. Please, bear with me. So another open question in black hole and jet physics, and especially in jet physics, even though these amazing objects are heavily studied across during many decades now, still we have a bunch of open questions, unanswered questions, like very fundamental ones, like how relativistic jets are launched, what accelerates these relativistic jets, how jets are confined and collimated, the origin of high energy emission, and also we see in these jets, by monitoring them, we see different components, different features moving. The nature of these features is not always straightforward. So putting all pieces of the puzzle together, many missions have and projects have started. One of them was building the Event Horizon Telescope, which its scientific goals were exactly this: to detect the photon ring around the supermassive black hole and try to tackle all these questions that I listed earlier about jets launched from supermassive black holes. Okay, the Event Horizon Telescope is a VLBI array operating at 1 millimeter. Is parted now more than, I think, 10 stations around the world. And employs the observational method of radio interferometry. I don't know how many people are familiar with this method today, so that's why I will give a very brief introduction about how what is this method and what benefits offer us observationally. So the main idea is that we observe bright sources in the sky that emit in radio waves and at 1 millimeter. In the case of the EHD, in general, it depends of what receivers we have. So we observe simultaneously from many antennas around the world the same object. Its radio station is equipped with an atomic clock, which ensures that we have a very accurate time stamp of the time that the light hit our antenna. The same, as I mentioned, the same object in the sky. And this gives us the advantage that we can later on collect the signal from each and every station, synchronize it, combine it, and create a signal equivalent with having an antenna as big as the Earth. Here in the corner of my screen, you can see this nice and elegant equation that describes us how we can increase our angular resolution. So how well and how can improve how well we can distinguish two objects or two features in a source or two features in the sky between them instead of seeing one. And this is impacted from the wavelength that we observe and the diameter of our collective surface from the observing instrument. So with this technique, we increase the diameter. As we mentioned, we have a radio telescope as big as the Earth. And at the same time, with EHD, we observed at 1 millimeter, 235 gigahertz, which means that we minimize this, so we can achieve resolution down to 18 micro arc seconds. This is tremendous, especially in these spatial scales close to these objects, and for active galactic nuclei that located near us, like M87 or Sagittarius star, the supermassive black hole in our own galaxy. This can actually reveal to us phenomena that we've never seen before. Honorary, just to remind that this type of data are very demanding and require a meticulous calibration, and later on imaging. And worth to mention there that besides the classic algorithm that we were used to image this data, which is clean, because of the EHT developed some complementary methods using different approaches, let's say, for the image reconstruction, such as the EHT imaging and SMILE and more RML methods or Bayesian imaging, which gives us additional angular resolution that further boost our understanding and our findings further. So by employing all these methods that I mentioned earlier, we managed to image with the Event Horizon Telescope, first time ever, a supermassive black hole, the photon ring around the supermassive black hole, and not only in the our neighboring AGN M87, also the supermassive black hole for our own galaxy. And these results, for these results, EHT got the Fundamental Breakthrough Prize soon after the publication of the results. But it's only that? No, having such a kind of instruments in our hands, astronomers have used it for studying AGN in general and advancing the jet physics. And here you can see a nice timeline since the first light of EHT until today, how many projects have been observed and finished and published because of that, and some complementary projects with the EHT observations. And now let's go to our object. One of these sources that EHT targeted besides the two that I mentioned, M87 and Sagittarius star, it was OJ27. And why OJ27? This is a legendary source because it's so far our best candidate to hosting a supermassive binary black hole system in its center. And why we say that? Because the last more than 800 years, it shows us a nice variability in the optical light curve, which corresponds with 12.2 years periodicity. And this corresponds to a theoretical model of a primary black hole in the center with a secondary supermassive black hole following an elliptical, a highly elliptical orbit around it, and passing through the accretion disk of a primary every 12 years. So every time that the secondary passes the accretion disk of the primary, we have an optical flare from thermal flare. Yes, and here we can see also a nice cartoon of this model. On top of that, the jet that we see in radio of this source is a puzzle itself, because we observe through time erratic jet precession. As we can see here, from year to year, the jet could look completely different. This behavior is there as long as we observe the source, and so far we have not a clear answer what is the cause of this phenomenology, because one can say, okay, this, if indeed we have a binary in the center, yes, comes from the binary, but in reality does not fit perfectly this scenario. And also the same phenomenology can be driven by King instabilities or if we have frame dragging, if we have a misaligned accretion disk, and because of this misalignment, we have a dragging of space-time around the supermassive black hole. So the whole jet, it follows the space-time medium, and we have this precession. So at the moment, we don't have a clear answer. We continue monitoring this behavior, and one day we hope we will have our answer. So as you understand, there is a lot to study in this source. That's why last years there are big campaigns, observational campaigns. And of course, having in our hands such instruments like EHT that gives us so extreme resolution would be ideal in order to see in spatial scales, very small spatial scales, to how the source looks like. So many instruments looked OJ27. In this talk today, we're gonna focus in the Event Horizon Telescope. That's are the most recent results. That's why I mentioned it, and the RadioAstron, which was an antenna, radio antenna, radio telescope orbiting Earth. And gave us also amazing results. And also complementary multi-wavelength campaigns, many multi-wavelength campaigns that have given us gives us amazing results and behavior of the source. I mean, it's a multi-wavelength emitter, so we see gamma ray activity. Also, OJ27 has given a TV flare in the past. Polarization, we have very interesting polarization swings there, and so on. And let's focus in the EHT observations back in 2017. So already from after getting data in our hands, we saw that the observations took place in 3 different sessions: April 5, April 10, and April 11. April 11, unfortunately, the UV coverage was not good enough, so these data were not good enough to proceed with imaging. But for April 5 and April 10, we had very satisfactory UV coverage, so we could already say that the source shows changes within 5 days, structural changes. This was something very new, and for this source, it was the first time seen. We proceed with, we followed the usual drill. We proceed with the imaging and confirmed what already we saw from data in our UV plot, that source clearly changes from within these 5 days. And also in polarization, we did the total intensity imaging and the polarization imaging, and we saw that the innermost jet structure is described but by very distinct components. I mean, in the innermost region, we have these 2 small components, C0A and C0B. One of them could be the VLBI core, but again, we are not absolutely sure. But on top of that, we have C1, C2, and C3. And C3 actually is a very interesting feature itself, because complementary observations with GMVA plus ALMA, again, April 2017, shows us that this feature corresponds to a recollimation shock, and actually in a textbook case, especially this bifurcation in total intensity and polarization corresponds to a recollimation shock. And in our EHT data, indeed, this fan-like structure of the EVPAs, again, is a signature of a recollimation shock. But on additional with the total intensity, the differences, structural differences in the total intensity structure, we saw that the P1 and P2 polarization components, the EVPAs changing as well within these 5 days. And actually, they changing in a different way each other. For instance, P1, it moves, the EVPAs move anti-clockwise, I think around 10 degrees, and P2 clockwise. This was something very, very new and puzzled us a lot and try to understand why this behavior is happening. And we realized that this happens because in jet is dominated, this plasma, relativistic plasma flow is dominated by a helical instability. So the perturbations P1 and P2 that we mentioned earlier, they are moving along this helical instability. And with this motion, they illuminate different phases of this instability. And that's why we see that in P1 has this motion, and P2 also this exact rotation. So this was something that we saw first time ever in the source, and now we know and we can check if we encounter the same behavior in another source that it's could be also the same behavior. Here we have a video, a nice animation actually, about what we saw for better understanding what happened in the source. So we have our components, the P1 and P2, sitting in the helical instability, and the whole jet is threatened by a helical magnetic field as well. So with the propagation of these instabilities, we have illumination of different phases of this region, and we saw this is reflected in the EVPAs of the source. Next, I would like to talk about another data set of this big campaign. So, as I mentioned, another powerful instrument that we had developed, it was RadioAstron. RadioAstron, it was a 10-meter antenna orbiting Earth and operating simultaneously with many radio stations in the ground. The resolution that actually RadioAstron could give us was more than EHT, because taking advantage of an antenna into space could correspond to baselines as big as 5 or even 15 times the Earth diameter. So because of that, we observed J27, of course, and actually we had some nice snapshot observations when the satellite, it was in its apogee, which gives us nice 15 Earth diameters resolution. And here, this data set gave us the highest resolution image ever of the source, which revealed a very complex innermost structure, as we can see here, and especially in comparison with GMVA 3 millimeter data and 15 gigahertz data. Further analysis of this data, of this image, showed us that the energetics of the source are very high. The brightness temperature reaches values of 10 to 13 power, which exceeds the physical limit. And this is explained from extreme Doppler boosting in these regions. And the Faraday, rotational measure analysis, rotational measure analysis of the source showed us some nice indications of a helical magnetic field, which later on saw also in the EHT data, and also from single disk observations was already there seen from other studies. Then 2 years later, of course, data are never enough. We observed again OJ27 with RadioAstron at K-band, again 22 gigahertz, like the 2014 data. This time, we didn't manage to have snapshot observations to see if something changed in the source, but we had regular observations with RadioAstron, which gave us a nice 47 microarc second resolution. Worth to say that in this experiment, many antennas managed to participate, specifically 27 antennas. We have a very nicely dense UV coverage here. The observations took place 25th of April 2016, and the imaging of this data showed us something very, very interesting. Well, until this point, until calibrating and seeing this data, the picture that we had, the high resolution image that we had for OJ27, it was the one that I showed you before, the EHT one, the small, this small, nice, this small, nice structure in the middle, a bit wobbling sometimes, but that's it. However, during 2016, exactly because, as we mentioned, the jet is precessing, it was a very lucky coincidence that the jet, it was pointing slightly away from us. And in combination with a very high SNR data, we managed to image segments of the jet that it was, they were invisible until that point. So we revealed, instead of this innermost region, we revealed a very nice ribbon-like structure with 3 very sharp bendings of the jet, extending down to 650 microarc second from the core, which is well inside the recollimation and acceleration zone. And we can see such a nice complexity. Here it's just a comparison plot to understand where this nice structure locates in the source. And brightness temperature analysis again showed very high values, and again it's because of extreme Doppler boosting. Here, just to demonstrate what we see until that point in 2016, and then after this RadioAstron data, we could see only the innermost region, and because of this now, the 2016, we know that there is way more structure there to see. With this information in our hands, we checked also the publicly available data from Boston University, and taking advantage this imaging method that I mentioned earlier, the EHT-IM, that can give us some more angular resolution than the classical clean method can give us, up to 3 times. Actually, we saw that the last years from 2014, the source actually is, the jet is actually precessing with this manner. So from 2014, we had this phenomenology. We could kind of see the extended part of the jet. Then in April 2015, again, only the innermost part. 2016, as I showed, again, the whole thing. 2017, back to the innermost region. So a nice visualization of this behavior.
Shake it, shake it.
Yeah, we couldn't imagine that there is probably a child hidden in the heart of this galaxy and playing with this jet, like the this cute kid in the video with the Who's. Yeah. And yes, our campaign now continues. More data are on the way from GMVA plus ALMA, from RadioAstron next years, and also from OJ27. But so far, we have reached this point that we now understand deeper the structure and the behavior of this source. About the and to add here that studying this precession of the jet, we compared it in our paper with the existing models of the binary system and partially confirm the model. So again, I mean, until now, still we cannot give a clear answer what could be the driver behind this precession. And I want to spend a bit of a small self-promoting moment here. Oh, my apologies. I want to shortly advertise another project that I'm leading with Event Horizon Telescope. It's about another source, very famous source, 3C454.3. In the past, it's in the past because of its very dramatic variability. They give her the nickname Crazy Diamond. So, for many years, it was the brightest gamma ray source in the sky. Hold the title of the brightest, being the brightest gamma ray source in the sky. I think now it's, yeah, I'm not sure if it's still now. Back in 2016, in May 2016, RadioAstron observed the source again with 31 antennas. Now I'm also leading this project, and I'm in a paper writing state that we have imaged this data, and the source shows very interesting jet morphology. As we see here, as you can see here, a very interesting perpendicular jet structure from what we consider as the normal flow of the jet. We are working on it. And for the EHT project that I mentioned, some years ago, I wrote this proposal and got EHT plus ALMA and observed the source in 2022 for the very first time ever with Event Horizon Telescope. Now I'm calibrating the data, and soon we're gonna have a first image of the source with EHT that we're gonna resolve this small region up here. And just as a fun fact, a few years ago, this was one of the sources that I studied during my PhD, and I studied the time range between 2013 and 2017, and by studying the kinematics of the source, realized that after 2014, the source was showing the appearance of new jet features, the new jet features from the core region that they were propagating. And once they were reaching this characteristic region here, we have called it region C. It's a very historical region, and it's there since the very first detection of the source with VLBI. The components appear to disappear. Suddenly they were nowhere. So, and this region corresponds to this interesting structure that I mentioned earlier. So we did this analysis, and we believe, and there are indications that here is a very extreme bending. So many interesting things are ahead. Stay tuned, and thank you very much.
Thank you very much, Thalia, for a fascinating talk. Are there questions? Don't be shy. Otherwise, I will start asking questions.
I have one question. Can I?
Yes, yes.
Thanks, Talia. Interesting talk. Um, I don't know if I understood correctly. During the first EHT campaign for OJ287, you said that there was variability within the campaign itself. So some days,
5 days, yeah.
5 days, right? So if I remember correctly, this same behavior, the EHT guys have seen it in Sagittarius A star, right?
Yes, yes,
And
absolutely.
that was attributed to scattering, if I'm not mistaken, just because we are observing down to our to the galactic disk. So do you think that it's the same? So what is happening in OJ27? Again, it's a scattering. Why is it varying within 5 days?
Um, I mean, it's definitely not scattering. For Sagittarius star, we see actually in the heart of our galaxy, and we see through our galaxy because we are trapped inside. So we have all this screen of intergalactic, interstellar, sorry, medium. In case of OJ27, we are looking in totally different directions, so we are not suffering of such a kind of effect. So it's a purely structural variability of the source.
So you need a very, very compact feature there happening
Yeah, yeah.
during that. Okay. Okay, thanks.
Any more questions? Okay, I'm curious about several things. Like one thing that comes to mind immediately. Okay, I think it's like very exciting results on OJ287 with EHT and RadioAstron that we really see like how the basically a helix would form. Like we see the jet bending like live, and we can even see like the temporal variability with the polarization direction, right? I found that very exciting. How does this relate to, let's say, a binary model or so? You said that this was inconsistent. It was consistent with Kevin Helmholtz instabilities where the components are traveling down there. But does this also like match more or less with predicted timescales from a binary model?
This is super fast for a binary to be driven for interaction between the two black holes. So no, it's not a longer scale periodicity of jet precession could align, but so fast no.
Yes. So the EHT is still not quite there when it comes to necessary resolution in time
No,
and
no,
space, right? So.
no. No, I think now the development of gravitational wave detections can actually give us this solid proof that if we are dealing with a binary there or not. But surprisingly, I saw last August Nanograv published this paper with OJ27 included. So far there's again, it's not a clear gravitational wave detection from the source or many other sources that we see a periodical variability in their emission. Let's see. Lisa or PTA.
Well, the when I heard PTA people talk about this, they kind of had it on the horizon to have more individual detections in a few years' time. And so, at least optimistically speaking, maybe we'll get there in a few years down the line. Yes.
We are so looking forward.
Unfortunately, I'm not in no position to accelerate that process, so I'm also just hoping.
Yeah.
Okay, that's great. Any more questions from the audience?
This is my
Okay.
cat.
Okay.
He
Well,
has
I
a
think
question. to my
Okay. Well, then I think we can finish for today. So thank you so much, Talia, for your exciting talk.
Thank you very much.
And but I would hope that you would be able to come by in person sometimes. I know you've been around before, right? So maybe we
Yeah,
can make that happen.
fingers crossed, I would be so happy.